Hello everyone and welcome to today's webinar. Today is the first webinar of a series on additive manufacturing. The topic today is how to minimize warpage of polymer and composite parts. My name is Shaba Juder, I'm Marketing Manager for Extreme Engineering, and I'm the host for today's webinar. Our presenter today is Philippe Hébert. He's a Digimat Product Manager. So there will be a Q&A session at the end of this presentation. If you have any questions, please type your question down in the Q&A and chat window, and we will try to get them answered during the Q&A session at the end or shortly after the webinar. So now I'm going to pass the presenter to Philippe.
Thank you, Shaba. So hello everyone, I'm very pleased to be here today with you for this webinar, which will be very application oriented. So we will have a look today how Digimat and the simulation solutions of Digimat can help for people doing additive manufacturing of polymer and composite parts, and on one specific pane, which is how to control the warpage to get the right dimensional accuracy. So we have three parts in this webinar. First, short introduction on the additive manufacturing of polymers and composites, just to give the right bit of context and show where we position in this field with Digimat. And then we'll have a look at how we can actually simulate the additive manufacturing process for polymers and composites. So this will be the most technical part of the presentation. And then, of course, this is all leading towards the objective of today's webinar, which is how to minimize warpage. So we will show how we can reduce and minimize the warpage of typical additive manufactured parts. And this will be done through a case study, but also a live demo. Okay, so first of all, let's have a few words on the additive manufacturing of polymers and composites. Also because additive manufacturing, even though it's growing very fast and there are many things happening, where we are looking at today is for polymer and composites on the material extrusion processes and on the powder bed fusion types of processes. So in other words, the FDM or FFF process for fused deposition modeling or fused filament fabrication, and selective laser sintering here. Okay, so this is what we mean today when we talk about additive manufacturing for Digimat. So I guess everyone is pretty much well aware of additive manufacturing and how it works. Just one quick word to say that, for instance, with the technologies such as fused deposition modeling, well, very complex parts can be built because we are not relying on subtractive methods, but we are adding material layer by layer. And adding this material layer by layer is a very nice way to achieve very challenging designs, but it's also introducing some more complexity in the manufacturing process, as we will see later on. But of course, the big challenge is to be able to handle those layer by layer deposition issues, and we will see how simulation can help to do so. Okay, so even though we are talking about both FDM and SLS, and they are completely different manufacturing processes, we can still talk about them in a very generic fashion because it's both additive techniques where we add material layer by layer. Okay. And one very important point also, just to mention why we are looking at those two specific techniques, it's also because they are the ones which are the most adopted in the industry. So we are not looking at the, let's say, rapid prototyping or personal usage pattern in the additive manufacturing industry, but really looking at industrial production type of application, like in the aerospace, automotive industry, or medical industry. Okay. And so, of course, these two technologies, they enable to work with unfilled polymers, but also with reinforced polymers, such as beads or fiber reinforced. And of course, this is where the material performance become very interesting, where we can actually have true functionality in the manufactured part. So the manufacturing industry is growing very fast. Although it's not a brand new industry, but it has some very recent interesting activities. But still, what we see is that there are still quite a few pains that hinder the development of additive manufacturing. You can see here results of studies conducted, for instance, by Stratasys, where the end users report a high cost of equipment as one issue that can have an impact on the AM market. Also, the mechanical properties that can be achieved through these techniques, which are either not sufficient or either very uncertain. And the third pain being the number of materials available for industrial type of applications. It's still quite low, and there is a need for sure to have an expanded material portfolio on the market. So those are really high-level pains. Now, if we go more onto the shop floor and have a look at what are the day-to-day pains, well, we find back some that we mentioned just before. But what we see also is that there is a really big question mark on the reliability of printed parts. So it's not always easy to achieve the right design accuracy because of warpage. So once you have printed your part is either out of tolerances, or if you actually have too much warpage during the build, you can have build issues that result in job abortions. Behind this warpage, there is also the notion of residual stresses. So those residual stresses are very important to consider because obviously they will have an effect on the part performance. So you can have part failure during the printing process because of too high residual stresses, or you can also have preferential failure after the printing step because of very high residual stresses. Okay, and so there are many other types of, let's say, issues that are hindering the reliability of printed parts, like what is the impact of the printing direction on the printing process, but also the part performance. What is the effect of all the process parameters, and there is quite a big list out there. So many still open questions. And what we want to focus on today is especially on the design accuracy for warpage. So we will have a look at how to minimize warpage of printed parts, and also, of course, the twin brother that goes hand in hand with warpage are residual stresses. So today, if you want to build a part with additive manufacturing, the actual workflow is to design the parts, actually print it. You may encounter printing issues like excessive warpage or excessive residual stresses. But if you have a successful print, then you end up, after some post-processing, with your final part that has a level of warpage, residual stresses, and maybe porosity. So if you want to know, does your part actually respect what was initially designed, well, there is no other solution than to test it. And usually it's not right from the first time, so you need to go back, change some process parameters, maybe change your printing strategy or even your material choice. And if this is not sufficient, you may even want to go back to actual the design step and then go again through the full workflow. So obviously this is not highly efficient, and what we want to do with DigiMat and simulation is to optimize this additive manufacturing workflow by inserting simulation prior to the actual printing, so that all the trial and errors that are done experimentally today or in the lab, they're actually done through simulation. And the simulation strategy is a highly coupled one that considers material, some material models, material behavior, process simulation, and structural performance. And once we are able to handle all these aspects in a predictive simulation framework, then proper optimization can be performed prior to the printing, so that the actual physical printing is done right the first time. Okay, so with Digimat, we want to address this optimized additive manufacturing workflow, and our solution for additive manufacturing is architectured around three key aspects of material engineering, process simulation, and part performance. So obviously, the main focus of today will be on the process simulation, and we will see how, through multi-scale modeling, we can predict warpage of printed parts for FFF and SLS. And so, as we are moving towards the simulation part of this presentation, of course, one interesting word to mention is that when we look at additive manufacturing and the type of phenomena that arise, the type of microstructures, the type of materials, well, we realize that there are many different scales involved. To have a look at the very generic FFF or FDM structure, you might have inside your parts lattice structures, so which actually define a given mesostructure. So you can have a very low infill to gain weight. In some other regions with dense rasters, you will have different way of depositing the beads. Okay, so you can see you have different mesostructures here, but inside one deposited bead, there are many things that also happen. So there is first the relationship between several deposited beads, so what is happening at the interface, but also what is happening inside the beads. You can have porosity, which is induced depending on the process, and you can also have, very important for high performance, fillers, so reinforcement like beads or fibers. Okay, so overall, there are many scales involved in additive manufacturing applications, and so if we want to simulate the additive manufacturing process and the additive manufactured part performance, we need to account for all these different scales. Okay, so obviously, as we will see in the next part of the presentation, multi-scale modeling is really what enables us to achieve and solve this problem. Okay, so now let's have a look at how we can simulate the additive manufacturing process. So the simulation of the additive manufacturing process relies on our core technology, which is material modeling, multi-scale modeling, and Feynman analysis. So this is historically where Extreme has been working since the past 14 years already. And if you see the Digimat platform, we have several products for additive manufacturing, some for material engineering, Digimat AM for the process modeling. This is what we'll be looking at today. And we also have the printed part performance. Okay. So what we want to look at today is Digimat AM for the process simulation, which is using the key technologies that you find also in the other Digimat products. So what is Digimat AM? It's our process simulation software from Extreme Engineering. Like we saw in the introduction, today we are considering two types of manufacturing processes, and those being selective laser sintering and fused filament fabrication, or FDM for part of the users. Okay, so those are the two types of manufacturing process that we can simulate inside Digimat AM. And in terms of materials, Digimat AM is dedicated to polymer-based materials. But what is interesting with polymers is that they can be reinforced. So we support both unfilled polymers, so let's say the most simple ones, but also the reinforced ones, reinforced with beads or fibers. So obviously, as soon as you add reinforcement inside the material, you add one scale in the material, in the way everything is happening in the deposition process. So it's adding more complexity, but also enabling to reach better performance. So the output of Digimat AM, or the goal, is to predict how manufacturing happens. And basically, the biggest interest for now we are looking at concerns the prediction of warpage and residual stresses. So in other words, what is the actual geometry of the part once it's printed compared to the geometry of the part as it was designed. And of course, as engineers, what we want to do is ensure that the printed geometry actually corresponds to the designed one, so that the part, once it's printed, can be used, for instance, in an assembly as it was expected. So what is the simulation workflow inside DigiMat AM? We'll have a look at it through a live demo at the end of this webinar. But just to give you already an insight, and this is applied to the FDM process, what we want to do is really to replicate as much as possible what is happening in real life. So the starting point in DigiMat AM to do the process simulation is to select your geometry as well as the material that you want to use. Okay, so this is really defining the component that you want to build, which is made of the geometry and the material. Now the next question is to say, how are you actually going to manufacture this part, this component? So with which printer and using which process parameters? So in the case of FDM or FFF, there is the notion of tool paths, which is very important, that describes how the material is being deposited everywhere, layer by layer. And so you can load this toolpath information that comes from your slicing software inside DigiMat AM, so that DigiMat AM can use it for the simulation. There are some process parameters describing the chamber, describing the heat fluxes that we may have, describing the deposition conditions. And once this is all defined, then the simulation can be run. So what will be simulated is the actual deposition of the beads. We will see afterwards that, of course, we cannot afford to simulate exactly the full manufacturing process bead by bead, but we have a very efficient multi-scale approach where we can actually do some pre-computation and then only simulate the layer by layer deposition. So after this simulation, what happens is that we obtain the residual stress distributions, material properties distributions, and very importantly, the final deformed shape. And so with this final deformed shape, we can either export it, and we will see it can be very useful to compensate for warpage, but we can also go further, and this will be widely discussed in the next webinar of this series. We can export many information to the actual parts performance. So if you want to do simulation of your parts performance, you will be very interested into knowing what are the residual stresses and how they affect the response of your part, what is the local tool path, and maybe some other information like porosities. So the process simulation inside DigiMat AM relies on a multi-scale two-step methodology. The idea is that if we want to have a quick and efficient way of simulating and solving the additive manufacturing problem, we want to act smart and try to separate the scales as much as possible, but also separate the physics. So what you see here on the bottom is a true full coupled thermal mechanical simulation that represents a small volume of material. Okay, so this is what we actually compute for all the representative regions of the printed parts. From this small but detailed simulation, we extract information about how material actually works, and then we can apply this layer by layer to the full structure. And this enables to solve the printing of the part in typically less than 1.5 hours, okay, starting from scratch. And we will see this also during the live demo a bit more how it works. Okay, so very efficient multi-scale methodology. Now the big question is obviously how does it perform? So here is an example of warpage prediction of DigiMat AM. We are looking here at selective laser sintering application. So it's actually a geometry which is used to calibrate a printer. So you can see it has a very distinctive geometry with all the steps and also very flat plate in the center, at the bottom, sorry. So this part was built using material from Solvay Engineering Plastics, the Technil Sinterline PA6. So it's a PA6 reinforced with 40% weight of glass beads. So it's already a very nicely engineered material. And we have simulated the actual printing of this part, but also measured experimentally what was the warpage after the part was printed. And what you can see is on the left-hand side, the warpage that is observed experimentally, so through a scan of the printed parts. And on the right-hand side, this is the prediction of Digimat AM. So we are looking here at the displacement. This is what is meant by the colors. You can see on the bottom the actual dispersion of the displacement. So this is really giving you the global view of the displacement, and you can see that the peak predicted by Digimat AM is on the right-hand side of 0.5 millimeters, while experimentally is slightly more to the left, but still pretty much in the right region. So same as the global trend, you can see we really have the biggest peak, which is here. And on some other aspects, you can see that, for instance, the warpage we observe at the corner of the plates here is quite well predicted also by Digimat AM. Okay, so overall, this multi-scale approach works very well to predict warpage. Okay, as we can see on this application. So this means that simulation can be used to predict warpage of the printed parts. And so the next question is obviously, how can we actually use this simulation to enable an optimization of the process and minimization of the warpage? So this is what we will see in this third part of the webinar. So how to minimize warpage with Digimat AM. So we can imagine actually several warpage control strategies. Inside Digimat AM, as we will see in the live demo, there are several steps where you can actually first define what you want to print. So what is your geometry, what is your material? Then how you will actually print it, so define your manufacturing. So what are your process settings, what is your tool path? Simulate everything you have defined previously and obtain as results warpage and resource stresses. So why I'm presenting it in this way is because we can see basically what are the entry points to the simulation and how the results can be used afterwards to minimize warpage. So one way to minimize the output of Digimat AM is to act on the definition step. So maybe try to adapt your material choice to minimize warpage. So one way to do so is, for instance, to add reinforcements in the material that will increase the stiffness of your material and also reduce the coefficient of thermal expansion. So changing the material composition is one way, one possible way to explore to minimize the warpage. Another one concerns the manufacturing step, where actually we can look at the influence of process settings like the chamber temperature, the extrusion temperature, the laser power, many possible process settings, and find the one that minimize the warpage of the component. Okay. But one last one is also to have a look at what is the warpage that occurs with a given material and with given process settings, and use this simulation result to actually compensate the initial geometry, so that once you print a compensated geometry, you obtain a warped part, but which actually corresponds as much as possible to the design geometry. And this third strategy is actually the most easy to set up, because it can be difficult to access to different types of materials. it can be tricky to enter into dozens and dozens of process settings. So that's why what we want to propose in the next few slides is a methodology to compensate for warpage. So the idea here is to minimize the warpage of the component that you can see here. So it's an engine bracket. We are looking at this part made by FFF with an ABS material. And what we want to do is have a printed geometry which is as close as possible to the as designed geometry. So the first step is to run a simulation of the manufacturing inside DigiMat AM. So as we will see in the live demo just afterwards, it's just a matter of defining the material, defining the way you want to print the parts, so what is the tool path, what are the process parameters, and then once you run the simulation, you will get the layer by layer deposition simulation and then the actual warpage prediction. And of course, what we see from the warpage prediction is that we have a very bad respect of the dimensional tolerance. We are actually completely out of the dimensional tolerances. And so we want to use this first simulation result to actually compensate for warpage. So here is a comparison of the as designed geometry, so the one that you have in mind and the one that you actually send to your printer. So it's the green one, and in red, the geometry that you actually get once you print your part. So obviously, the as printed part does not respect the geometry of the design part. And with this application, where you can see you have areas dedicated to bolts, it seems quite obvious that the part as printed now will not be able to be used in an assembly, for instance. So what we want to do is compensate for warpage. So once you have simulated the manufacturing process and obtained the warpage prediction inside DigiMat AM, you can export a counter-warp geometry. So you get an STL file. And based on this counter-warp geometry, you simply restart the printing simulation. And what you will see is that indeed it will enable to get much closer to the design geometry. Okay, so once you have exported the compensated geometry, you go back through your slicing step, if you're doing FFF, for instance, enter in DigiMat AM, run the manufacturing simulation, and get a new warpage prediction. So of course, here what we are looking at is warpage prediction compared to the counter warp geometry. But once we compare the warp geometry here in the second step to the design geometry, what we see is that we are getting much closer. Okay, so that's what is summarized on the slide here. So before compensation, as we saw before, the as designed geometry and the as printed geometry are very different, and this is very problematic. But once you print the compensated geometry instead of the design geometry, you can see that the as printed geometry becomes very close to the as designed one. Okay, so if you want to then print your part for real, instead of printing your as designed geometry, simply use the compensated geometry that is obtained from DigiMat AM, and you will have a much better design accuracy. Okay, so now I'd like just to show you this process live inside DigiMat AM. Okay, so here we are inside the software. You can find back the 4 steps that we saw previously, so the definition, manufacturing, simulation, and results. So let's start by the definition step. We'll be working here with an SLS printer, and let's directly define the components. So I will load my STL file. Okay, we can find back the engine bracket. Okay, here we are. And last step to define my component is to select the material I want to use. So we have a database inside DigiMat AM for some materials. You can see here, for instance, the polyamide reinforced with glass beads from solvent-driven plastics. But if you want to create your own material with whatever filler you want, whatever type of material for the matrix and for the reinforcement, or just for the matrix, it's also fully possible. Okay. So now we have the printer and the components completely defined. We can go to the manufacturing step. Here, it will be actually quite simple. We will keep the default process parameters for this material, but if you want to adapt the part positioning, the layer thickness, the chamber temperature, laser powder, and so on, it's of course possible. And then we can directly go to the solver step. Okay. So on the solver step, what we want to do is first create a Feynman model for this geometry, because we will solve the printing simulation through Feynman analysis. So you can choose different levels of mesh size or use a custom one. Okay, we will see here we can easily obtain a voxel mesh, which is very convenient to get a layer by layer discretization of the component. Okay, and then last step in the solver before running the job is actually to specify what is the material model and what are all the material properties. So remember, what we are doing is a multi-scale approach where first we do the actual printing of a small volume of material. And so for this, we need very detailed information of, let's say, quite basic properties, but along the full range of temperatures that are encountered during the manufacturing. So we want to know what is the evolution of the Young's modulus over temperature, the evolution of the CTE for the matrix, for the reinforcements. We want to know information about specific heat capacity, thermal conductivity, and so on. Okay, once we have all these information set up, you can just submit your job. You can see that there are two steps here, the pre-processing, which is the computation at the RV level, representative volume element. So this typically takes something like 1 hour, but once it's done, you don't have to simulate it anymore, except if you have changed some material and process settings. And then you will have the actual warpage simulation, which is very fast because it's purely a mechanical analysis. Okay, so I will not go through the job submission here. I will have a look at results that are directly obtained. Okay, so what we see here are results from the simulation. So we can have a look at the deflection, at the stresses that we have after the part has been built. And actually here we are at the very last step where supports have been removed, so the part is really completely freed. Okay, but if we want to look at what is happening during the printing process, it's also possible. Okay, so obviously there is changes happening inside the material during the printing, but also once we cool the part at the end. Okay, so we can also visualize on the geometry if we want. And if we look at what is the warpage that we get here, well, we see it's quite significant. We have almost 3.5 millimeters of deflection, so which is obviously very, very significant. So one way to judge whether your warpage is too high is to have a look at the warpage indicator. So this will simply compare a warpage critical value to the actual warpage that you have locally. So let's say you have a 1 millimeter tolerance, which is obviously too high. You can see where this tolerance is respected or not. Okay, so red is bad, green is good, and yellow is let's be careful. Okay, so what do we do from here? Well, obviously we're not satisfied by the way the part was printed here. So what we propose is to export the warp geometry. Okay, and we can play with scale factor for the warp geometry. So not only we can just say export what we see here, but you could say export the counter warp geometry, so simply put -1, or a value which is close to -1. This will allow to compensate for warpage in the initial geometry. Okay, so that's what we want to do. Just before, I'd like to show you a more detailed comparison of the designed and printed geometries. Here in green, this is the actual geometry that we want to print. Okay, and in red, this is what is predicted as the warp shaped by Digimat AM. Okay, so we can see that it's really not good. Okay, there is a lot of shrinkage, but also a bit of warpage. And if we look, for instance, at how the holes align, it's very bad. Let's say it this way. Okay. So what we want to do now is rerun the simulation, but using the counter-warped geometry that we exported. Okay. So in the manufacturing step, what we can do is work for warpage compensation. So either apply a scale factor on the geometry. Okay. So say how you want to scale your geometry in the X, Y, and Z directions, or load a modified geometry. So if you load counter-warped geometry that was previously exported from Digimat AM, you can then run the full simulation again. Okay, and here the pre-processing step is already done, so it's very fast to get the actual warpage prediction. Okay, and what we see from this run on the compensated geometry is that, of course, we still get warpage because that's what happened during the manufacturing process. But if we compare to the reference geometry, so the actual geometry that was defined at the component, we can see that warpage, instead of having a maximum value around 3.5, if I have a look at this warpage expressed compared to the reference geometry, we're going down to much lower values. Okay, so here the highest values that we get are 0.8 millimeters compared to 3.5 prior to the warpage correction. Okay, so if we come back to the warpage indicator, let's say we still have a warpage critical value of 1 millimeter. If we have a look on the printed part, it's very bad, okay, because we have warpage occurring. But since we want to compare to the reference geometry, we can see that afterwards, everywhere we are going below a local warpage value of 1 millimeter. So in other words, we have significantly reduced the warpage of the part. And so just to compare also the geometry, the warp geometry after compensation, so the one we are looking at here in the second step, you can see that we go from this configuration, okay, where we have obviously not the right geometry, to a warp geometry, so a printed geometry, which is here in red. Okay, so very nice improvement. So you can see it's still not perfect, so there might still be one or two iterations that need to be performed, but it's improving a lot the warpage that we get. Okay, so in summary, the Digimat AM simulation approach for an optimal printing is to add the simulation prior to your physical printing process, do virtual printing, predict your warpage, export the countered warp shape, run through your printer pre-processing again, especially for FFF if you need to slice your part again, perform your virtual printing, and then obtain an improved warpage behavior compared to your initial design. Okay. And so you might want to iterate and do several loops. The good news is that this is a highly efficient process, so the iteration loop can happen in less than 1 hour because the simulation approach is very efficient through the multi-scale modeling. So conclusions for today's webinar. I hoped I delivered the message that simulation and multi-scale simulations such as the one proposed by DGMAT can really help to unleash the true potential of additive manufacturing. So additive manufacturing is proposing such an amazing way of building products that cannot be built in a different way. But if we are not able to really control how the part is built and how the part performs, then we cannot actually reach the full potential of additive manufacturing. But with simulation, we can actually control what is happening. So we hope that simulation can really help to unleash this full potential. Through DGMAT AM and the process simulation that we have, we are able to predict and optimize the additive manufacturing process for polymers and composites. We saw here how we could optimize warpage for glass bead reinforced polyamide components. And so, of course, this is not the full story if we want to unleash the full potential of additive manufacturing. If you want to further optimize your additive manufacturing design process, you don't want to stick to can I print my part and does it correspond to the geometry that I was expecting, but you also want to know how does my part actually behave? Can I optimize the performance of my part in terms of stiffness, of strength, etc. And so this is really key to further optimize the design process, to connect manufacturing to structural performance. And so this is basically what we'll be discussing in the next webinar of this webinar series. So that's it for today. If you have any questions, I would be very happy to answer. And
thank you very much, Philippe, for this very informative session. So we have, we'll take a few minutes to take questions. So we have one actually already. Is there a function built in the software to suggest design changes to reduce internal stresses?
So today, I wouldn't call this a function, so it's not automated. But what you can do is use DGMAT AM to predict the result stresses and perform, for instance, a design of experiments. So try several configurations, and from there, identify what are the right design choices to make. But it's not yet fully automated. But obviously, this is a direction we want to take, so that you just have to press on a button and you can find directly what is the right design, or what is the right material choice, or what are the right process parameters.
Philippe, another question. I do not understand very well how you can take into account the real tool path and between brackets G-code file.
So what happens in our simulation software in the solver is that once you import a toolpath file, let me check, I might have an example here. I would just switch to FFF. Okay. Okay, this is not perfect, but I hope it will give some illustration. Okay, so if you have your J-code file and you load it inside DGMAT AM, what will happen is that per element inside the voxel mesh that we get, we know exactly how material is being deposited. Okay, so is it plus minus 45 degrees, or is it fully aligned, or is it something else? Okay, and depending on how the material is being deposited inside each element of the voxel mesh. Okay, so let's create quickly a voxel mesh. This is, of course, very much too coarse, but it means that DGMAT AM knows in each element what is the deposition pattern, and based on this information, it will compute the right simulation of the representative volume element that we saw in the beginning of the presentation. Okay, so that means that we identify what is the local printing pattern everywhere throughout the part. Of course, this is not something that you see here on the screen, but based on the different patterns that we have everywhere throughout the part, we will apply the right inherent strengths that we have pre-computed.
Okay, so we have two more questions, so we'll take these two last questions. Philippe, okay, one is, can we simulate warpage for only solid parts using Digimat? Have you considered the impact of using infill percentage on part warpage?
Yes, absolutely. So what we show here in this first version of Digimat AM is dedicated to, I would say 100% type of infills, especially for FFF. So if you have something like, let's say 20, 30, or 40% infill, obviously this changes the way warpage is happening. So we have pragmatic solutions to work on this, like knockdown factors on the material properties. But basically what is happening is that right now we are working so that in the future this will be fully supported. Okay. The key is really just to represent the right deposition pattern in the pre-computation. So this is the only thing that we need to do. So we have this in the pipe.
And the last question, what are future solutions other than warpage? How does Digimat MF, FE combine for solutions to AM?
So we have to distinguish three types of modules inside Digimat for additive manufacturing. Here what we are looking at, Digimat AM is for process simulation. So it's really all about understanding how a part can be built, what is the warpage, what are the result stresses that build up, but also, let's say in the near future, what is the porosity that is happening everywhere, or what are some other microstructural effects. But then if you want to relate this to material behavior and understand, well, does it affect the stiffness or the strength of my material? This is indeed happening inside MF and FE. Okay, so Digimat MF and FE, they are the modules to do material engineering, so characterization of the material properties as a function of the constituent and the microstructure. Okay, so if you know what is the microstructure that is set by your manufacturing process, Digimat MF and FE can tell you what is the material properties that result from this microstructure. And then if you want to simulate the part performance, so let's imagine this bracket which is under service loads. We will use Digimat MF and FE as material models for structural analysis with Feynman analysis like in Abacus, Mark, ANSYS, or whatever. And this will help you to do the part performance. Okay, so maybe I can find back the summary slides. Okay, so MF, FE, and NX is really about material engineering, MAP CAE, and we are working also on Digimat RPs for the printed part performance, and Digimat AM is for the process simulation. So those are obviously working hand in hand. AM predicting how the material is deposited and what is the microstructure that we get. MF, FE tell you what is the material response as a function of the microstructure, and MAP and CAE allow to transfer all this information to the full structure to do Feynman analysis as usual.
Thank you, Philippe. So if you want to hear more about Digimat additive manufacturing, we have two more webinars coming up. One on the 3rd of July and another one in September, so 7th of September, but you will receive invitation emails from us. So thank you very much for joining this webinar today. Thank you very much, Philippe, for presenting this very informative session, and we'll see you at the next webinar. Thank you.
Thanks, everyone. Bye-bye.
Bye-bye.